Welcome to Algebra 1 with Miss Betsy. Today we're going to be talking about how we express square roots, both with a radical symbol and by using fractional exponents. Before we get started, though, I'm going to go ahead and step out of the way. What we have on the board behind me is a very quick review of how you deal with graphing equations of lines and creating equations of lines, and this is something that I've been doing with one of my kids. Thought I'd go ahead and leave this screenshot up here for you just for a moment because it's a good review. We've got the two, and I realize I'm out of the screen, but we've got the two basic equations, forms of a line that we're going to use the most commonly. We have the slope-intercept form of a line, which is y is equal to mx plus b. We have the point-slope form of a line, which is y minus y sub 1 is equal to m times x minus x sub 1. M always represents the slope of the line. Here, b is the y-intercept. And here, x sub 1, y sub 1 represents any random point. Over on the right-hand side of the board is an example where we were given 2 points, and they said come up with the equation of the line and then go ahead and graph that line. Little reminders here that when the instructions ask you to write something in slope-intercept form, what they're asking you to do is solve for y, and frequently when they're asking you to come up with the equation of a line or to graph a line, they'll give you just 2 points like they did over here in this example. So I've stepped out of the way of that long enough so that you can pause your video if you wish to pick up this little bit of a review here. And in order for a point to, 2 ways that you can tell that a point is the slope-intercept. Obviously, if they tell you that a given number is the intercept, I said the slope-intercept, I meant just the intercept. If they say the y-intercept is -4, you know exactly where that's located. Otherwise, the y-intercept is always going to have the form 0y. So, what we're going to do now in Chapter 10.1 of the second edition of Algebra 1 for Christian Schools that's published by Bob Jones University Press, what we're going to do is we're going to see that we can also find the roots of a number by using fractional exponents along with the radical signs. And I've got some notes here. This is on page 396 of this text. This is the second edition. If you're using the third edition or another book, you need to be real careful. Make sure that you're following the right information. For my kids who are in the current class right now, make sure that you spend a good amount of time working on this section on your own. There's a lot of information here that you need to be able to understand what they're talking about. Also, you can go back to chapter 2.6 in your book or to that earlier video and review just basically what square roots are. But real quick, a square root of a number, we're looking for one of the numbers for numbers 2 equal factors. And those factors can either be positive or they can be negative, because you can say that 3 times 3 is equal to 9. You can also say that -3 times -3 is equal to 9. We talk about something that's called the principal square root. When you simply use this radical symbol here, this means that they are asking for the positive square root. So the positive square root is the principal square root. Not principal, a square root. If they want the negative square root, they're going to indicate that by putting a negative sign in front of the radical symbol. You also remember that I've asked you to memorize the perfect squares of numbers up to 400. What perfect squares are there? Well, up to 400, that would be 1 squared is 1, 2 squared is 4, 3 squared is 9. For example, 10 squared is 100, 12 squared is 144. 15 squared is 15 times 15 is 225. 20 squared is 400. And what you're going to see is that the square roots of these perfect squares are the only ones that have a rational root. Now, what's a rational number? Remember that a rational number is something that can be written as a ratio of, with a numerator and a denominator. So the square root of 400 is equal to 20. Okay, square root of 4 is 2. The square root of 9 is 3, but you cannot write, and these are rational numbers because they can be written in a ratio with the form of a numerator and a denominator. 2 can be written as 2 over 1. Square root of 7, though, all of these numbers that are not perfect squares, when you take their square roots, they're irrational numbers. And you need to remember that irrational numbers are numbers that are non-terminating, non-repeating decimals. And some examples of those irrational numbers that we've talked about in class, an example would be pi. Pi is an irrational number, and you learned earlier in your math career that pi was equal to 3.14. Well, pi isn't equal to 3.14. Pi is approximately equal to 3.14. That's an approximation. You know, pi is about 3.14. And then you might have moved along a little bit further. You said, oh, no, like some of my kids have said, no, pi is equal to 3.1415. Well, that's a little bit closer. But I can say no, pi is 3.1415926. What it is this number, this decimal number goes on forever. It doesn't terminate, meaning it doesn't end. And there's never a repeatable pattern in there. So what you need to know is that all of the square roots that are not perfect squares, they are irrational. So it's not possible to come up with an exact answer for the square root of 8. If you say, you can approximate and say the square root is between this integer and that integer, or you can use your calculator, put in 8, and then press the key on your calculator, that is the square root key, 8 times the square root of x, and that's going to give you a decimal approximation of it. But this right here would be what we call the exact notation for the square root of 8. Let's see what else I have in here. You know, just to reiterate, you can never write out an exact decimal representation of a non-perfect square. You can approximate it by rounding to any number, just like for pi. We can't exactly say what pi is, but if I ask you to round to estimate pi to the nearest hundredth, 3.141, we have tenths, hundredths, thousandths. Pi estimated to rounded to the nearest hundredth would be 4. How about this? 3.14159. What if we wanted to round to the nearest 10th, 100th, 1000th, 10,000? And then we're going to look to the digit to the right of it. And pi rounded to the nearest 10,000th is approximately 3.1416. So they're just wanting you to make sure that you can differentiate amongst some of this vocabulary. The principal square root of a number, or the principal square root of a number positive, is positive, and you cannot give the exact answer, the exact representation of the root of a number, of the square root of a number that's not a perfect square. Review of some vocabulary or some how you write things. If you have something inside here, inside this radical symbol, this radical sign, this is called the radicand, and the number up here is called the index. We have a radical sign, we have the radicand, and we have the index. And what you need to know is that if the index is not visible, it's a 2. What's the index here? It's a 2 because it's the square root. Okay? Now let's say that we wanted to estimate the value of a non-perfect square root. We already know that the square root of 25 is 5. We know that the square root of 10 is 100. We know that the square root of 100 is 10. The square root of 25 is 5. The square root of 144 is 12. But what is the square root of 129? What is it? Well, first, 129 is not a perfect square. So we are not going to be able to come up with an answer that is exactly the answer that we're looking for. We're going to have to come up with an approximation. There are 2 ways that we can come up with the approximation. So we need an approximation. First, we can use our calculator. Calculator. And I did not bring my calculator, but what you're going to do is you are going to punch in 129, and then you're going to hit your square root key, and that's going to give you something like 11.238714. I honestly have no idea what it's going to be, but it's going to be a little bit more than 11. It's going to be less than 12. And it's going to be closer to 11 than it is for 12. So this right here would be your approximate value of what the square root of 129 is. So, square root of 129 is about this. Or you could come up with which 2 integers the square root of 129 lies between. So what you're looking for is you are looking to sandwich this number between 2 perfect squares. And this is why it's so valuable to to have on the tip of your tongue, or right here in the forefront of your memory, the value of the first 20 perfect squares. So you're looking for perfect squares that are the closest to 129. 10 squared is 100. 11 squared is 121. So 11 squared is 121. 121 is less than 129. Well, if we have 11 squared here, what's 12 squared? 12 squared is 144. So your first step in approximating the square root of a number, or in finding, when it says estimate, this is an exact quote from the book. This is example 2. Estimate the square root of 129 to the nearest integer. We're going to border that, or sandwich 129 between 2 numbers that are perfect squares. And we're going to order them correctly. 121 is less than 129, which is also less than 144. So if that's true, then we can also apply the same operation to each piece of that, and we say the square root of 121 is less than the square root of 129, which is less than the square root of 144. Square root of 121 is 11, which is less than the square root of 129, which is less than 12. And this is how we would write the answer to the problem. Estimate the square root of 129 to the nearest integer. This is to the nearest integer. This is if you need to estimate a square root, or any root for that matter. If you need to estimate a root to a specific decimal place, that's when you're going to use your calculator. Let me see. Cannot emphasize it enough. If you don't know your perfect squares at this point, it's long past time for you to do that. So go ahead and invest half an hour, 10 minutes, whatever you need to do to get those square roots memorized. So this was still pretty much, should have been pretty much of a review to you. Now what we're seeing is that we can express roots of a number rather than using a radical symbol. We can use fractional exponents. It's another way of expressing radicals. Guys, you've got to study your book on this. Whatever text you're using, you're going to need to study your book on this because it's just weird algebra speak. And I'm just going to illustrate this for you. If we have b and the radical symbol x to the a, this is using radical symbol notation, and this is read really, really, really weird. Every time I try to record it, I end up laughing. I'm not going to... Okay, I am going to laugh this time because I'm sorry, I just think it sounds silly. Just like, you know, you have the square root of 4, you have the cube root of a, you have the fourth root of 16. Well, when it's b, they say that they say that you have the bth root of age, and I realize that's really not that funny. It just strikes me as funny. It's dumb sounding. The bth root of x to the a, and all that means is this is the pattern that you're going to use to translate from radical symbol to fractional exponential notation. And the way that that works is what do we have in here? This is the radicand. This is the exponent. This is the index. The index is before in the radical, and it's on the bottom, or it's beneath in the index. I just said that this radical symbol is going to, we're going to see another way that we can express that using a fractional exponent. The b is before the radical, it's beneath in the exponent. So that's how your index and exponent translate here. So if we have the cube root of 8 squared, we can write that as a fractional exponent. The radicand is the base. The index, which is before the radical symbol, is also beneath the fraction bar, or it is the bottom. And the exponent is the numerator. The cube root of 8 squared is the same as x to the 2/3. The square root of 4, well, what's the index and what's the exponent? this would be 4. What's that index right here? The index isn't visible, it's a 2. If the exponent isn't visible, it's 1. So 4 to the 1/2. What you're going to see as you use it more and more frequently is a fractional exponent of 1/2 is the square root. A fractional exponent of 1/3 is the cube root. Okay? Now, what if we had been given the instruction, and I'm jumping ahead now, to simplify the square root of 4 using exponents? Well, we've got an exponent here, but can we write this 4 as an exponent? Sure. Isn't that the square root? The square root of 2 squared? Isn't it true that 2 used as a factor twice is 4? Okay, that's true. So the square root of 4 and the square root of 2 squared represent the same value. Now, using our rules for indicating roots with fractional exponents, the 2 is our base. The number inside here, the exponent, is our numerator. And the index here, which is a 2, is our denominator. So we have we have 2 to the 2 over 2. Well, any number divided by itself is 1, isn't it? So that would be 2 to the first. And 2 to the first, we just understand that that factor is only used once. So we end up with 2. The square root of 2 squared is equal to 2. Just as we know that the square root of 4 is also equal to 2. Alright? This is just a little bit weird. You need to be able to go back and forth. If you're given a value where you have an exponent that is fractional, you need to realize that we're indicating some sort of a root. You need to be able to go back and forth equally comfortably. Translate from one form into another form. Trust me on this, if you only watch this video or if you glance at it just for a second and you don't practice, you're going to get tripped up in this because it's not something that we naturally know how to speak. Many of us were around parents and extended family and friends who spoke well and spoke frequently, so we recognize, most of us, that it's not correct English to say we was going to go fix us some dinner. We recognize that that's not correct grammatically, and it just jumps out at us. Many of us, the incorrect grammar jumps out at us. Incorrect algebraic notation is not going to jump out at you until you have really taken the time to acquaint yourself with it. Make sure you study. Okay. Remember, the index is always 2 for square roots, and an exponent is always 1 if it's not written. Now, what are cube roots? Remember that cube roots, we're looking for 3 equal factors whose product is the radicand. The cube root of 8. We know that's 2 because we're looking for 3 equal factors. Here we have 3 factors that are the same, 2 times 2 times 2, and their product is 8, which is that number right there, which is the radicand. So example 3 on your book was asking you to do very similar to what we did where I simplified the square root of 4 using exponential notation. Let's just go ahead and do example 3 it says to simplify the cube root of 8 using exponential notation. And what they're saying here is use fractional exponents to help you. Use fractional exponents. So the cube root of 8, we're going to change that 8 into exponential notation because 8 can be expressed as 2 cubed. Now we're going to see what we can do with this. We're going to go from notation that uses a radical symbol to fractional notation. To a fractional exponent. We've got a numerator and a denominator. And what is the denominator, or what is the bottom of that numerator? It's the index. And the exponent is the numerator. So we have 2 to the 3 over 3. There's just a lot of speech in it. It just sounds silly, but that's read. 2 to the 3 over 3. What is 3 divided by 3, or what is any number divided by itself? That's equal to 1. So you now have 2 to the first. What is 2 to the first? Anything to the first power. We understand that 2 is used as a factor one time, and we don't need to show that. So here we have simplified the cube root of 8 using exponential notation by going from the cube root of 8, writing that as 2 cubed, translating that into fractional exponent notation here, recognizing that 2 to the first is the same as 2. And of course, the cube root of 8 is 2. At this point, you know that. But this is a way that they're wanting you to verify and to show that you understand how to use fractional exponents. Okay, let's see what else I have here. Now, we're going to, remember I said we've got to be able to go back and forth. This is example 4. Not example 4. Example 4, and we have 3 to the 1/3 x to the 2/3. And you're going to look at that and your eyes might cross a little bit and you think, that's just really crazy looking. And it is. Let's see, this is example 4 on page 398, and it says, change this to radical form. We want to write this in radical form. There is no work to show. It's just an understanding and an application of how radical form and fractional exponential form work together. We have two factors here that have the same base. I'm sorry, not the same base. Two factors here. We have a base of 3 and a base of x. But the two factors have the same bottom number, or the same denominator. Where does that bottom number come when you're using radical symbol notation? That bottom number is the index. It comes before you write the radical sign. These numbers here, the bases, these make up the radicand. So we have 3x. And the numerators of the corresponding factor here, the numerators are the exponents. So we have a 3 to the first, we have an x squared. Do we need to show that 1? As a matter of fact, should we show that 1? No. So what we have is the cube root of 3x squared. There is no work whatsoever to show on a problem like this. What you have to have internalized and what you have to be able to go back and forth of is that the bth root of x to the a is equivalent to x to the a over b. That's what we've done here, is we have taken fractional exponential notation and converted it back to the radical notation. Okay? Take the time to make sure that you can go back and forth and understand what's being done there. It really, honestly is. Can you follow this generic formula here, this pattern for what the numbers need to look like? And not only can you follow it, but can you use it? All right, we have another example. This is example 5. I have it written as example 4 on my notes, but I'm sure it's example 5. We want to change the 5th root of 4x cubed y squared to exponential form. How are we going to do this? We're going from radical to exponential. Our general pattern for radical form was the bth root of x to the a is equal to x to the a over b, not p, x to the a over b. It looks weird and it sounds stranger, but that's what we have here. We have the bth root, b is 5, x to the a. We're going to translate it. So what root are we taking? We're taking the 5th root. The index comes before the radical. The index is before the radical and at the bottom of the exponent. These right here, the 4 and the x and the y, are our factors. So we have a 4xy. Each one of these has its own fractional exponent, because what we actually have is 4 times x times y. What is the denominator? It's a 5. What's the numerator of this fraction? Every single one of these are going to be fractional exponents, and I'm going to leave myself some space. What's the numerator for the 4? It's this exponent here. It's understood to be 1. So we have 4 to the 1/5, x to the how many fifths? What's the exponent? It's a 3. So it's x to the 3/5 and y to the 2/5. It's cumbersome and it's strange looking, but there are times on head where it will be of supreme value to you to be able to express your roots using fractional exponents. That's why they're teaching it to you now. You think this is just ridiculous. We're writing something 2 different ways, and when am I going to use it? Right now you're not. But before too long you will. It's important to be able to translate roots into exponents. Okay? And then the last thing that they wanted to show you is, just like we learned how to come up with an integer approximation for square roots, we can also come up with an integer approximation for cube roots. Our last example was, give the integer approximation for the cube root of 50. So what we want to do is sandwich this 50 between two numbers that are perfect cubes. So we don't learn near as many perfect cubes as we did for square roots, but if you can know them 1 through 6, that's very valuable. 2 cubed is 8. 3 cubed, 3 times 3 is 9, times 3 is 27. 3 cubed is 27. 4 cubed is 16 times 3 is 64. 5 cubed is 125, and 6 cubed is, I believe, 216. 36 times 6, yes. 216. 2 cubed is 8. Which of these cubes does 50 fall between, or between which of these cubes does 50 lie? Comes right in here between 27 and 64. And it's closer to 64, so it's going to be more than 3.5. So 27 is less than 50, which is less than 64. We can take the cube root of all three of these numbers, and we retain the truth of the relationship between the three numbers, which is that the cube root of 27 is less than the cube root of 50, which is also less than the cube root of 64. Then we put in our integers. Cube root of 27 is 3, which is less than the cube root of 50, which is less than 4. And this is our answer, and this tells us that the cube root of 50 lies between 3 and 4. So that's the end of section 10.1. Make sure that you allow enough time for you to fully understand this material. And I'll see you on Friday.